Section 11.3, we're going to be looking at the areas of regular polygons. Remember, regular means that all of the sides are the same and all of the angles are the same. As we go through our new vocabulary surrounding this section, we need to refer to this picture right here. To start, we have the center and radius of the polygon, so this point right here is the same as the center and radius of its circumscribed circles. Remember, circumscribed just means that we're going to put a circle around the polygon, and each vertex of the polygon will be touching the circle. So the radius of the circle that's around the polygon is the same as the radius as the polygon. Also, the center of the circle is the same as the center of the polygon. The distance from the center to any side, so from the center to the side, so the blue line is called the apothem. And note that the apothem is perpendicular to the side of the polygon. So the apothem always has to be the perpendicular distance from the center to the side of the polygon. And while looking at this picture, do you see how we have a triangle right here? Therefore, it would be an isosceles triangle because the radius here and the radius here would be the same. So we have an isosceles triangle, so therefore the apothem ends up being the height of the triangle from the center to the base down here. So again, we have an isosceles triangle because the radius here and the radius here would be the same, and the apothem, the blue line, would be the height from the center of the polygon to the side of the polygon. It'd be the height to the base of that isosceles triangle. So once again, the apothem is also the height to the base of an isosceles triangle. So again, the apothem here is the blue line, is the height of this isosceles triangle, where the two legs of the isosceles triangle are actually the radius of the polygon. So one more time, the apothem is also the height to the base of an isosceles triangle. So the height to the base of this isosceles triangle that has two radii, so the two red lines here, as its legs. Next we have a central angle of a regular polygon is an angle formed by two radii drawn to consecutive vertices of the polygon. So referring to our picture, M and N are consecutive vertices of the polygon since they go in order. So therefore, this angle, MPN, would be a central angle because it is formed by the two radii, so the two red lines, of those two consecutive vertices of the polygon. So therefore, this right here, angle MPN, is a central angle, just like it states here in the green. Since this is a six-sided figure, 1, 2, 3, 4, 5, 6, there would be 6 central angles like this. Because there would be 6 radii, 1, 2, 3, 4, 5, 6, so therefore there would be 1, 2, 3, 4, 5, 6 central angles. So if I wanted to find the measure of one of them, I know that if I add up all 6 of them, I would get 360. So to find the measure of one of them, I would take 360 divided by the number of sides of the polygon. So again, to find the measure of each central angle, divide 360 by the number of sides of the polygon. So if it's an 8-sided figure, I would take 360 divided by 8. If it's a 10-sided figure, I would take 360 divided by 10. Make sure you write this down in your notes. To find the measure of a central angle, divide 360 by the number of sides in the polygon. Let's look at our first example. It says, in the diagram, RSTUVWXY is a regular octagon, so we have 8 sides, inscribed in circle C. Find each angle measure. For part A, they want us to find the measure of angle RCY. So RCY would be this angle formed right here. That would be a central angle since 2 radii are connecting 2 consecutive vertices of the octagon. So therefore, I would take 360, since it goes in a circle here, I would take 360 divided by the number of sides. So since it's an octagon, we have 8 sides. So again, I would take 360 divided by 8 to find the measure of that central angle. So 360 divided by 8 is equal to 45. So the measure of that central angle is 45. The measure of each central angle in this octagon would be 45. So therefore, if I drew two more radii connecting consecutive vertices, so like this, the measure of this central angle would also be 45. Moving on to part B, the measure of angle RCZ. So RCZ would be from here, here to here. Well, we know that this angle is 45 degrees and the apothem, the distance from the center to the side of the polygon, the octagon, would be bisecting that angle. So therefore, if this full thing is 45, half of 45 is 22.5. So again, I just took the measure of the central angle divided by 2, since the apothem would bisect that angle, so I would get 22.5. So far I have this right triangle in here, and I know that this angle here, which is corresponding to this angle right there, is equal to 22.5. So in part C, when they want us to find the measure of angle ZYC, which is this angle right here, ZYC, so we're looking for this angle right here, would be equal to 180, since I have a right triangle, minus 90 minus the 22.5. Therefore, I would end up with 67.5. So again, this angle right here is 67.5. So I first found the measure of the central angle by taking 360 divided by the number of sides. Since it was an octagon, I divided by 8. So the central angle was 45. I knew that the apothem bisected that angle. So to find the measure of half of that, I just took 45 divided by 2. Then I knew that a right triangle was formed, so I took 180, the number of degrees in an entire triangle, minus the 90, minus the 22.5 to find the 67.5 for this angle down here, like we were asked to find in part C. And now we come to our first theorem, theorem 11.4, the area of a regular polygon. The area of a regular n-gon with side length S is 1/2 the product, so we're going to multiply, of the apothem and the perimeter. So this is what I want you to write down in your notes, that the area of a regular polygon is A equals 1/2 times the apothem times the perimeter. And again, the big P stands for the perimeter. And the apothem is that A value. So to find the area of a regular polygon, it has to be a regular polygon. This only works if the polygon is regular. Is 1/2 times the apothem times the perimeter. Now let's look at example number 2. You are tiling a floor with ceramic regular hexagons with side length 8 inches. What is the area that a tile will cover? We know that we're going to end up using that formula. The area is equal to 1/2 the apothem times the perimeter of the polygon. Next, let's draw a picture to wrap our heads around what we're dealing with. So it's a regular, meaning all sides are the same, hexagon, so 6 sides. And we know that each side is 8 inches long. So what we have to be able to find is the apothem, that's the distance from the center, perpendicular down to a side of the polygon, and we also need to know the perimeter. We can find the perimeter right off the bat since we know that each side is 8 inches long. So since we have 6 sides and each side is 8 inches, we know the perimeter is 48. However, we're going to have to do some work to find that apothem. So notice that if we go from the center to the side of the polygon, the hexagon, we are making a right triangle with the radius of the polygon as well. We also know that if this side length is 8, the apothem is splitting that side into 2 congruent pieces. So we know that this side is 4. And again, we are trying to find the apothem length right here. So if we knew what type of triangle this is, we could figure out what that length is by doing either like a 45, 45, 90, a 30, 60, 90, or we could even do sine, cosine, or tangent. So let's now find this angle measure so we can start to see what kind of right triangle we're dealing with. So remember, if I want to find the central angle, like from here to here, this angle that's formed right there, I take the 360 degrees that's all the way around, divided by the number of sides, which in this case would be 6, since we would have 6 central angles. So a central angle would be equal to 360 divided by the 6 sides that we have. So 360 divided by 6 is 60 degrees. So if the central angle is 60 degrees, and the apothem not only bisects this side, but also bisects that angle, that means that this angle right here is 30 degrees, which means that this would have to be 60, and we'd have a 30, 60, 90 right triangle. So we need to remember those formulas. We know that the side across from the 30 degrees is the short side, and the long side is the side across from the 60 degree angle. So we have that formula that the long side is equal to the short side times the square root of 3. So if the short side, which is across from the 30, is 4, the long side, which we have as the apothem, the long side is the apothem, would be 4 times the square root of 3. So to complete our formula now, A equals 1/2 apothem times perimeter, we would have A equals 1/2 times the apothem, which is 4 square root of 3, times the perimeter, which was 8. So just to simplify, we would have half of 4 is 2. 2 times 48 is 96, so we would have 96 square root of 3 as our final exact answer, so that'd be inches squared. However, if you're really talking about the area of a regular hexagon that you're using to tile a floor, you wouldn't answer somebody as 96 square root of 3. So you would want to get a decimal approximation by putting it into your calculator. So 96 times the square root of 3 is approximately equal to 166.3 square inches. So again, that would be our final answer. The 96 square root of 3 is our exact answer, and 166.3 is our approximate answer. Example number 3, find the perimeter and the area of the regular polygon. In part A, we were given a pentagon, 1, 2, 3, 4, 5, and we're supposed to find the perimeter and the area. We'll have to start with the perimeter first, since the area is 1/2 the apothem times the perimeter. So again, we have to have the perimeter first to then use it in our area formula. Looking at the diagram, I see that we're given the apothem, since we know it's the distance from the center to the side of the polygon. So the apothem would be 6.5. I also see that we're given the radius of the polygon, but we are trying to find a side length to not only just find the perimeter, but then to use that answer to find the area. So we need to find a side length of this pentagon. Knowing that the apothem cuts the side length in half, if we can find this length first, then I could just double it to find one of the side lengths. Knowing that the apothem and the radius form a right triangle, I can use everything I know about right triangles to find this missing side length. Since I know 2 sides of the right triangle, I can just use the Pythagorean theorem to find the third side. And in this case, we'd be finding a leg length, not the hypotenuse. We were given the hypotenuse. So again, I can find this leg length by using the Pythagorean theorem. So whenever you're given 2 sides of the right triangle, use the Pythagorean theorem. Therefore, we would have x squared, the side length we don't know, plus 6.5 squared equals 8 squared. So I would square the 6.5 and the 8 to get x squared plus 42.25 equals 64. Subtract the 42.25 from the 64 to get x squared equals 21.75, and then to get x by itself, I would take the square root. So x would be about 4.7. So if this length right here is about 4.7, then I would just again double it to find one side length of our pentagon. So one side length would be about 9.4, and since it's a pentagon, I have 5 of those 9.4 lengths. So the perimeter would be about, and I'm using the about symbol since I rounded down here. I know that each side length is approximately 9.4, so the perimeter is going to also be an approximate measurement. So again, I have 5 side lengths, so 5 times 9.4 is about 47. So now we're going to take our area formula like we had from before, 1/2 the apothem, which we know the apothem is 6.5, times the perimeter, which we now know is about 47. So again, I'm going to use the approximate symbol. Since I'm not using an exact answer for the perimeter, then my area is not going to be an exact answer. So 1/2 times 6.5, the apothem, times 47, the perimeter, is about 152.75. It didn't give us a unit, so we could just say units squared. So again, let's walk back through this. We were given the apothem, but not a side length. So we first found half of the side length by doing the Pythagorean theorem, since we were given 2 side lengths of that right triangle. Once we found what this length is, we doubled it to find 1 side length, to then use that to find the perimeter. Then we took our answer for the perimeter in our area formula, times the apothem times 1/2 to find our final answer of 152.75. Now let's look at part B. Still the same directions. We're finding the perimeter and we're finding the area of this regular polygon. There are 10 sides, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we are told that 1 side length is 7. So we can automatically find the perimeter by just taking that side length times the number of sides. So the perimeter in this case was a lot easier than last time. We can just automatically say that the perimeter is 70 units long. But for the area, we not only need the perimeter, but we also need the apothem, which we are not given in this case. So let's figure out what the apothem will be. So I'm going to first draw it in. So we know that the apothem starts in the center of the polygon and goes straight down perpendicular to one of the sides. So we know that a right triangle is formed by the apothem here and the radius of the circle here. Therefore, we'll be able to use some right triangle trigonometry or special right triangles or wherever the case may be in order to find the apothem right here. We also know that the apothem splits this side length in half. So from here to here would be 3.5. Sometimes it's useful to take this right triangle and just draw it bigger so that we can identify things more clearly in a bigger picture. So again, we're working towards trying to find that apothem. So if I was able to find this angle measure, I could then use like a special right triangle, like a 45, 45, 90 or 30, 60, 90 like we did before, or I could use Pythagorean theorem if I had 2 side lengths, but in this case only have 1 side length, or I could use trigonometry, so like sine, cosine, or tangent. So in this case, let's figure out what this angle would be to then create a plan of how to find that apothem. So we know that the apothem splits a central angle in half. So to find a central angle, I'm going to take 360 divided by the number of sides. So again, 360 degrees divided by the 10 central angles there would be, since there's 10 sides. So each central angle is 36. But once again, the apothem splits that angle in half. So that angle measure would be half of that. So 36 divided by 2 is 18. So if this is 18 degrees right here, that means I'm going to have to use trigonometry, because an 18-degree angle right here is not a special right triangle. And again, we cannot use the Pythagorean theorem because we were not given 2 side lengths. And I would write down something in your notes about why we have to use trigonometry in this case, because again, we weren't given 2 side lengths in order to use the Pythagorean theorem, and since we had an 18-degree angle measure, that is not a special right triangle. It's not a 45, 45, 90, and it's not a 30, 60, 90. So again, that's why we're going to have to use sine, cosine, or tangent. So if this is 18 degrees right here, the 3.5 is opposite the 18 degrees, and the apothem is adjacent to the 18 degrees. So opposite over adjacent means we're going to use the tangent function to find our apothem. So the tangent of 18 degrees would be 3.5 over the apothem A. So since our variable is on the denominator, then we're going to multiply by A and then divide by the tangent. So the apothem would be equal to 3.5 divided by the tangent of 18 degrees, which is approximately equal to 10.8. So now we have all of our missing pieces. We know the perimeter is 70, and we know the apothem is about 10.8. So to find the area, we would take 1/2 times the apothem 10.8 times the perimeter. And I'm going to say that it's approximately this much since we rounded to find the apothem. That means my area is not an exact answer. So again, 1/2 times 10.8 times 70 is equal to approximately 378. So again, the perimeter is 70 and the area is about 378 units squared. And now on to another example, part C. Again, we're finding the perimeter and we're finding the area. So when I look at this, I see that I have a triangle, so 3 sides, and we are given the apothem. So the apothem would be 5. What I'm not given is a side length. So remember, if I can find this length right here, then I can double it to find one full side length. So what I'm going to do is create this right triangle in here so I can then use some right triangle trigonometry or special right triangles or the Pythagorean theorem in order to find this length here, which we're going to call x, just like we did before. So the Pythagorean theorem is out since I'm only given one side length. And now if we find this angle in here, then I can tell whether or not it's going to be a special right triangle or a situation where I'm going to have to use trigonometry. So remember, I find this angle by finding the central angle measure, which means I'm going to take 360, since remember this polygon is inscribed inside of a circle, and there's 360 degrees in a circle, and since I would have 3 central angles, because there would be one right here, and one here, I would take 360 divided by the number of sides, so therefore one central angle in this case for this regular triangle would be 120 degrees. So if one central angle, like this, is 120 degrees, then the apothem cuts that central angle in half, so therefore this angle in here would be 60 degrees. And once again, I find it's easier if I just take this right triangle and redraw it so I have a bigger picture to deal with, so I can better fill in what I know and what I need to find out. So if that angle is 60 degrees and I know the apothem is 5, and I'm trying to find this length down here, since I know that if I find this length, I know the apothem bisects one full side. So if I just figure out what this length is, I would double it to find the total length of one side of the triangle, which again, I need to not only find the perimeter, but also to find the area. So since this is 60 degrees, that means I have a 30, 60, 90 special right triangle. And the side opposite the 30 degrees is the short side, and the long side is across from the 60-degree angle. So it's the long side that I'm trying to find. I know that the long side of a 30, 60, 90 is the short side times the square root of 3. So the long side is what we're trying to find, so that's x. We just assign that as x, times the short side, which is 5, which is our apothem, times the square root of 3. So therefore, if this length right here is 5 square root of 3, we need to double it to find the total length of one side of our regular triangle. So one full side would be equal to 2 times the 5 square root of 3. So therefore, 2 times 5 is 10, so we would have 10 square root of 3 as one side length of our triangle. So if I'm trying to find the perimeter, I have 3 sides, and each side is 10 square root of 3. So therefore, our exact answer would be 30 square root of 3, or our approximation would be about 52.0 units, and then our area would be 1/2 times the apothem, which was 5, times the perimeter, which I'm just going to keep it as exact as I can until the very end. So I'm going to put 30 square root of 3 into my formula. So I would do 1/2 times 5 times 30 and then stick the square root of 3 on the end of that. I can multiply this 1/2 at any time that I want, so I would do half of 30 is 15, 15 times 5 is 75, so my exact answer would be 75 square root of 3, which is approximately 129.9 squared units. So again, we have our perimeter, which is about 52.0, and our area, which is about 129.9. And here is our last example, number 4. A regular decagon, which is 10 sides, is inscribed in a circle with a radius 8 units. So this length right here is 8, just like it's labeled. Find the perimeter and the area of the decagon. So similar to what we were doing before, except this time, if you notice, the only length that we were given was the radius. We are not given a side length, and we're not given the apothem. So to find the perimeter, I need to find at least one side length, and then I would just multiply by 10 since it's a decagon. And I also need to find the apothem to use in our area equals 1/2 apothem times perimeter. So let's start by recognizing that we have a right triangle in here formed by the apothem, half the side length, and the radius. So let's draw that right triangle so we can label it a little bit better on a bigger picture. So we know we need to find the apothem, and we need to find this length here. And then don't forget to double it, because again, if we find this length here, we know the apothem bisects one side length. So once I know what this length is, I would just double it for the total length. So let's find this angle measure so we know what kind of right triangle we're dealing with. So remember, we find this angle measure by first finding one central angle. The central angle will be found by taking 360 divided by the total number of sides, which is 10. So each central angle is 36 degrees. And remember, the apothem bisects the central angle. So if I'm looking for this angle here, which corresponds to this angle right here, I would take 36 divided by 2, which is 18. So that means that we are working with a right triangle with an 18-degree angle measure. So this is not going to be a special right triangle problem, and it's not a Pythagorean theorem problem since I'm only given one side length. So therefore, we're going to have to use trigonometry. So that means we're going to have to use sine, cosine, and or tangent. I'm saying and or tangent since we have to actually find two side lengths. We are given that this length is 8, which would be the hypotenuse. So that means I'm going to use sine and cosine since they are the only two that have the hypotenuse in it. So again, this is the hypotenuse. Let's look for the apothem first. So the apothem is adjacent to the 18 degrees. So cosine is adjacent over hypotenuse. So let's set up our equation. It would be the cosine of 18 degrees is equal to A, the apothem that we don't have, the adjacent side, over the hypotenuse, which is 8. Since our variable is on top, all we're going to do is one step problem multiply by 8. So the apothem would be 8 times the cosine of 18 degrees. Let's get a decimal approximation. So typing that into the calculator, we get the apothem is about 7.6 units. Next, let's find this side length, which would be opposite the 18 degrees. And again, we're going off of what we're given. So we were given the hypotenuse, so opposite over hypotenuse is sine. So setting up our equation, it would be the sine of 18 degrees is our missing side length, x, over the hypotenuse of 8. Once again, our variable is on top, so it's going to take one step to get the variable by itself. So our missing side length, x, would be equal to 8 times the sine of 18 degrees, which is approximately equal to 2.5. So if this side length right here is 2.5, remember we have to double it to find one side length of the polygon. So if this is 2.5, one side length, let's call it S, would be 5. So to find the perimeter, we would take the 10 sides that we have times the side length of 5 that we found. Since I rounded to get this 2.5, I'm going to say the perimeter is about 50 units long. And for the area, we're going to do 1/2 times the apothem, which we found was 7.6, times the perimeter, which we found is 50. And again, I'm going to say A is approximately this much because I rounded to get the 7.6 apothem, and I rounded to get the 50 unit perimeter. So again, A is approximately 190 square units. So let's circle our answers. Our perimeter was about 50, and our area was about 190. Let's wrap this very complicated section up with a concept summary. Finding lengths in a regular n-gon. To find the area of a regular n-gon with radius r, you may need to first find the apothem, like we were doing, or the side length s. So here's what you have to use. You can use the Pythagorean theorem when you know n, the number of sides, and two measures, either the radius and the apothem or the radius and a side length. And if you need to see an example of this, you can look at example number 2 and guided practice example number 3 in your book. So all of these are examples in your book, not from the notes. You can use special right triangles when you know you have n, the number of sides, and any one measure. So if you have r, the radius, or a, the apothem, or s, the side length, and the value of n, so the number of sides is either 3, so if you have a triangle, 4 if you have a quadrilateral, or 6 if you have a hexagon. So you will have special right triangles if you have a triangle, a quadrilateral, or a hexagon. And if you need to see an example like that in the book, look at guided practice example number 5. You will need to use trigonometry if you have any one measure, because remember, you could use the Pythagorean theorem if you have two measures, but if you have one measure and it's not a special right triangle, so it's not a triangle, it's not a quadrilateral, and it's not a hexagon, then you are going to use trigonometry. So again, any one measure, so if you're given the radius, the apothem, or one of the side lengths. If you need to see an example of it, then look at example number 3 and guided practice examples 4 and 5. And again, all of these are in the book, not the notes. And believe it or not, this very complicated section is now over. Make sure you write down anything that you need to be explained so that we can talk about it in class, and we'll see you then.